Now, I know it's going to sound a bit like a cliche, but it's sort of true, in that everything regarding design and engineering is a bit of a compromise. And case in point is this gear pump, which I recently made. And it's not so much the pump itself, but sort of how I'm using it. As I previously showed, the gearbox on this lathe, which I really like, unfortunately has no oil filter, which feels to me like a bit of a design oversight, because after you use it for a bit of time, all the wear particles get deposited into the oil, and then fed directly back into the gears, into the bearings and the oil seals, which really can't be good for them. So before I rebuild the lathe and sink $200 to $300 into bearings, I'm looking to add an oil filter to clean up the oil and hopefully prevent this thing from happening again. Which is kind of where the pump comes in. I know the pump itself is a bit basic to look at, but now that I've swapped the gaskets, it's a nice little pump, which squeezes perfectly into a bit of unused space in the cabinet behind the lathe. And even outside of spacing, I think in most ways that you look at it, this sort of pump is perfect for this job. I mean, it's compact, it was very easy to make, it was easy to mount, it should be low maintenance, very easy to drive, and low in vibrations. I mean, whichever way you look at it, it is perfect. Except for one problem. Because it's a gear pump, it is a two-directional pump, which means if we turn the input in the opposite direction, it will pump whatever it's pumping in the opposite direction. In a perfect setup, what you want is the oil to go from the gearbox to the filter to the pump and then back to the gearbox, in that order, and really only in that order. And speaking of filter, I'm simply using a standard automotive filter to clean up the oil. You know, they're cheap, they're super easy to get, and they work. And in terms of the order of operations, having the pump come after the filter is pretty standard. One, because you don't want the pump to be pulling through contaminated oil and wearing out the pump, because it is a precision part, but also because automotive oil filters usually have an inbuilt check valve to stop the backflowing of oil. So what this means is that if we place the pump after the oil filter, it should pretty much guarantee that the pump stays primed. I mean, if we set it up the other way, it should stay primed, but doing it this way should be a better guarantee. And because gear pumps are pretty rubbish at self-priming, I always want the motor to have oil in it when it's running. Now the reason why I'm telling you this is that when the lathe is running in reverse, the pump is also going to be running in reverse and sending oil in the wrong direction, and there's really only two things that will happen here. One is that the pump runs dry and causes excessive wear to the pump, which is not something that I want, and number two is that it causes enough back pressure that it either blows some of the tubing off or causes some damage to the one-way valve. And long term, either scenario is not good. Now of course some of you did recognise that this was going to be an issue that I was going to run into, and some of you suggested that I run a more traditional single or double acting pump operated by some sort of camshaft so that no matter which direction the pump is running, it only pushes oil in one direction. And I think that's a great idea, but I think having an eccentric load spinning at about 1200 RPM might cause us some problems with regards to vibrations and how it may impact the surface finish on parts. Plus, I think it would be a bit more difficult to install that in this confined space. Some other people also suggested running a separate motor for the pump, which is pretty fair and it would solve a lot of the problems that I'm going to run into, but it would mean mounting the pump somewhere else and of course having to power it separately, and of course that would mean having to wire up 12 volt power because the lathe only has 240 volt. And to be completely honest, I really like the idea of powering all this from the single motor that drives the whole lathe. And being able to neatly package it in that empty space there is really the cherry on top. It is a bigger challenge, but I really like the idea of doing it this way. So my solution, at least in theory, should be quite straightforward. What I'm going to do is run a simple one-way bypass line around the pump. So during normal operation, it won't be used. The oil will be pulled from the filter to the pump and then back to the gearbox. However, when it's put into reverse, the oil, since it can't pass back through the filter since there's a one-way valve, what it will do instead is flow through a bypass line, through another one-way valve and join up back at the intake, essentially creating one big loop. There should be no excess pressure and the pump should stay oiled. Of course that sounds simple enough on paper, but with a tight packaging here, it really wasn't. And unfortunately my very simple plan became a lot more complicated than intended. You'll see why. First things first though, we need to ditch the aluminium intake barbs. They're the wrong material for this and they're the wrong shape. What I need here is a compact T intersection and the off-the-shelf ones were simply too big to use. So I'll be swapping over to using brass, which I can solder to make a T-joint. It'll probably cause some problems with galvanic corrosion, brass on aluminium and all that, but it's nothing we can't address later on. Anyway, the barbs that I'm making here should be similar to the previous ones, just a little bit longer with a T intersection. And that's what the barbs should look like. Unfortunately, in testing it, there was something that I did overlook, and that's the tube that I'm using can't bend on such a tight radius. So I'll have to go back and extend it by 10mm, which is really at the limit of how long I can make these. Now I won't drill the barbs just yet because first we need to address another problem which I've encountered, and that's even with the longer pieces of brass, I've just checked the length of the check valve which I was going to use, and unfortunately it's 60mm long. And unfortunately, given the space limitations, I simply don't have the space to work with that. So at this point I think it's pretty obvious that we're going to have to do all of this fully custom. So given that this has just become a high precision job, I'll first start off by ripping off the 3-jaw and get the collet chuck put on. I've gone out and bought some 20mm brass, which I'll use as the main body of the one-way valve. So the first thing I'll do is face off the end and get the end turned down for some threads. The threads that I'm going to make are M18 by 1. It's not really a standard thread type, but all of this is custom, so as long as they all fit together, that'll be just fine. And what I really need here is a fine pitch, small thread. I'll then bore out the end with an end mill to create a flat bottom hole. I'll then come in with the boring bar and then open it up. The space here is going to be used for a rubber membrane. I'll then get it parted and then do roughly the same thing on the other side, although not as deep. And finally, I'll drill a hole in the center, which will get tapped for M3. Before I do that though, I'll get it in the mill and use that hole to locate the center of the part. The plan here is to drill 6 holes around the outside, and this will be for the oil to be able to flow through from one side to the other. I think technically what I'd probably rather want are arcs rather than holes, but I'm on a manual mill and I don't have a rotary table, so drilling holes is about as good as I'm going to get. And because there's not enough space to get my spotting drill in, I'll start off the hole with my carbide end mill and then follow it up with a drill bit. Alright, and that is looking pretty good. What I need to make now are some end caps with a nozzle built in, and because I was aiming to make this as compact as possible, I originally wanted the threads to run up as close to the end of the bore as possible. And really, the only way to do that would be to use a tap with no lead in or taper. And of course, because all of this is custom, I'd need to make a tap to be able to do that. Now the good thing is, I've made quite a lot of taps before in the past, but the only problem here is that to make a tap you need high carbon steel, and I don't currently have any high carbon steel large enough to make a tap. So the tap that you're seeing me make now is made from mild steel, which isn't really what you want because you can't really harden it, but I've used mild steel to cut aluminium and plastic before on tons of occasions without issue, although never on brass, so let's find out together. I'm not really expecting much from it, but it only needs to work twice for it to be a success. The geometry is good, so let's see if it cuts. Well, it was a bit of a long shot, but I guess brass is one step too far for mild steel. Unfortunately, all I really did was just flatten the cutting edge and deform the brass. Now at this point, I could case harden it and take it all the way to about Rockwell 60, but doing it that way would take about 4 hours in the furnace, plus a few extra hours for prep and cooling down. So instead what I'll do is I'll add an extra 5mm to the part length and single point thread cut it. Doing it this way will take us to the absolute limit of allowable length, but we should be able to get away with it. And because I don't want the tool to crash into the part, I'll simply spin the chuck by hand. And despite it being a bit deformed from trying to tap it earlier, it fits very nicely on the middle section. I can now part it off and then do the same for the other side. And with each side now made, I'll take down the ends to form the nozzle section. And once it's all assembled, it'll look something like this. I know it does look a bit plain, but most importantly, it's less than 50mm long, which is the target that we're trying to squeeze under. But before we go any further, we do need to address the non-return valve part of it. Now, if I had a bit more length to work with, and maybe an assortment of ball bearings to choose from, I probably would have gone for a ball check valve. The design that I settled on to use eventually though, was to use a diaphragm type check valve, which I've worked with in the past, although not in this particular application. And the design of them is pretty simple and straightforward. A thin piece of rubber is seated up against the brass face with the drilled holes. When there's oil pressure pushing up against it, it'll push the diaphragm up against the brass surface, which will block the flow of oil. However, when there's oil coming from the other direction, through the holes, it'll push against the rubber, flexing it outwards, allowing oil to flow around it in one direction only. Now for this to work, the rubber needs to be thin and the fit between the rubber and the barrel needs to be pretty good. Now making the diaphragm, I was tempted to make a stamp to cut it out, but after about 10 attempts with trying to cut one out with a blade, I eventually got one that didn't leak around the edges. And to keep it held in, I'm going to be using an M3 screw. It's also worth adding that the material that I used was 1mm thick nitrile rubber. Nitrile rubber should be a good fit because oil won't attack it, but unfortunately even 1mm is kind of too thick even for this. So I have gone ahead and ordered some 0.5mm nitrile rubber sheeting, and the plan is to replace the diaphragm with it once it arrives. Even still, with the wrong size of material, it still does work. I know it is a bit of a lousy demo, but I'm blowing in one end and you can hear air coming through the other end. But when I swap the directions, you can't hear any air coming out the end. It is a bit of a lousy demo, you'll see it in action in a little bit. Before we can do that though, we do need some 90-degree joiners to create the bends. And to keep this as compact as possible, I'll do this all in brass and then solder it up. So over at the lathe, I'll make the male pipe connector. I'll then take it over to the mill and then bore into it so I can join it up to the one-way valve. And this is how everything should go together. I'll then remove the diaphragm so I can get it all soldered up. And after a bit of clean out, that turned out sort of how that turned out. The important thing is that it's oil tight and there's no gaps. And that should sit on top like so. So the final thing left to do now is mark out the positions of the connectors and then get them drilled and soldered in. And once it's all assembled, it'll look like so. I know it does look a bit more like a Franken build than I was expecting, although then again, I really wasn't expecting to be building all of this. So all things considered, I'm happy that I was able to make it, at least small enough to all fit in. The real question is though, does it work? So I'll set it up with the cordless drill and prime the pump. I'm not exactly sure how to properly bleed a bypass with a one-way valve like this, so we may have to deal with a few air bubbles. So far though, under normal running conditions, it's running just as fine as it did previously. Good oil flow and no leaking so far. The real question though is what happens if I pinch the inlet tube and then cycle it backwards? Will the bypass line work? And thankfully, to my relief, it worked. Worked well even, for about 5 seconds. Thankfully though, it wasn't a big problem. I simply forgot to add a hose clamp. Okay, again, something still ain't right. Okay, rather embarrassingly, it wasn't the fault of the one-way valve. I accidentally installed it back to front. And with it properly installed, finally it works. And it works pretty well. Given that the rubber is a little bit too thick, there is a bit more pressure in it than I would have wanted. But once that's replaced, I'm sure that we will see a big drop in the pressure. But even with the wrong thickness of rubber, it's working pretty well. I know it is a bit difficult to see, but you can see that when I close off the tubing, the oil is moving up through the tubing into the non-return valve. Essentially, it's doing one big loop, and it's not pulling any new oil into the tubing. I know we are seeing some air bubbles move past, but that's not indicative of any large amounts of oil moving past it. So I guess for all intents and purposes, this should be perfect for the final build. I know that it was a bit more effort than I really wanted, but for what I need, it'll be perfect. And as for the final build, let's start making that soon. Until then though, thank you very much for watching, I hope you enjoyed this video, and I will see you next time.